The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
All right. Today I would like to start by discussing a timeline. And you'll see in a moment what this timeline has to do with. It's obviously only a partial timeline, but let's start here in 1916, as we have done this semester, by talking about the Lewis structure of theory of electronic structure. And his electron pair theory is something we're going to come back to a couple times during lecture today. Let's move on to 1954. 1954 was an important year in electronic structure theory because in that year there was awarded to Linus Pauling the Nobel Prize in Chemistry. So let me write down Pauling here. And if you're interested in knowing something about what Pauling was awarded the Nobel Prize in Chemistry for, I'll show you over here on the sideboards. Where you'll see, if it's possible to dim the lights in front just a little bit, that would be helpful. Can we do that? Dim these front lights a little bit, possibly? Okay, what you're going to see here, if you read this citation for Linus Carl Pauling in 1954 for the Nobel Prize in Chemistry, his prize was awarded principally for his contributions to our understanding of the nature of the chemical bond. If you think back to the elegant title of the paper by Lewis that we started out our discussion of acid-base theory with, it was a paper entitled The Atom and the Molecule. And now we've got to Pauling in 1954, who is being awarded a Nobel Prize in Chemistry for the nature of the chemical bond. That also is the title of a very famous chemistry book by Linus Pauling, the book entitled The Nature of the Chemical Bond. That was published by Cornell University Press originally because it stemmed from his set of lectures at Cornell, the Baker Lectures, in the 1950s. So as we talk about electronic structure theory, I'd like you to keep in mind the way in which these different great geniuses were approaching the problem, a problem that we're going to launch in on today and spend the next few lectures on. We'll move up here to 1966. And in 1966, there was awarded a Nobel Prize to Mulliken. Not to be confused with Millikan. Mulliken, and let's see if I can bring this over here to work with it for a moment. So we're going from 1954 to 1966. You're going to find, as you explore the Nobel Prize website, that there are a lot of informational links on these people. You can go and read biographies. You can read some of their writings. In the case of Linus Pauling, you have links to all the pages of all of his research notebooks, spanning more than 60 years of research. So those are pretty interesting supportive materials. in the case of Robert S. Mulliken, he's being cited for his contributions to the molecular orbital method, which we'll also call the molecular orbital theory. So we have Lewis theory. We have, in the case of Pauling, I'm going to say the nature of the chemical bond described in terms of valence bond theory. We'll come back to that in a moment. And then in the case of Mulliken, we've got a Nobel Prize for molecular orbital theory. And I just would like to show you something kind of neat here. This has to do with the fact that if I go to the section labeled Other Resources, I can click on MIT Digital Thesis Library, and then I can choose a page of Mulliken's thesis to display. And that is because Robert S. Mulliken was Course 5, 1917. So let's hear it for Course 5 Chemistry. Okay? Yeah. Robert S. Mulliken was one of you guys, and he graduated in 1917. His thesis at MIT, his undergraduate chemistry thesis, was entitled The Effect of Structure on the Activity of the Hydroxyl Group in Alcohols. So, submitted by Robert S. Mulliken. There's his signature. Okay, so isn't it cool to have your undergraduate thesis linked in from the Nobel Prize website? That's Robert S. Mulliken for molecular orbital theory. And you can see, even as you read his undergraduate thesis, he was talking about the effect of structure on the activity of the hydroxyl group. So he had the idea that if you knew something about the structure of the molecule, even back then, you could make predictions about the properties of the molecules. And that's what we really want to be able to do in chemistry, because we want to be able to control function as much as possible. And take that away for now. And we'll come back in a moment, because I'm going to mention to you that in 1998, there was another Nobel Prize given for advances in our understanding of electronic structure of molecules. And this one was a shared prize rather than these three other ones that I mentioned that were, well, two others. Lewis was neglected from that category, unfortunately. But in 1998, Cohn and Popel shared the Nobel Prize for furthering our understanding of how to describe electronic structure of molecules. And this is a theory that we're not going to be talking about too much explicitly here in 511-2 this semester, but if you go on in chemistry, you're going to get exposed to it more and more. It's called density functional theory, and it's one of the most expedient ways to use computers to get electronic structure information about molecules. And so that method has become extremely important, and I'll just show you a little piece of information from that website. So we go to 1998, and under the John Popel section, I'm going to go to interview, and he has given an interview on different topics relating to his involvement in chemistry. One short piece of that interview is entitled Interest in Quantum Mechanics and Development of Computer Techniques. So we're going to take a look at that, and hopefully, if the audio and video are both working, you'll be able to see John Popel talking a little bit about this important area of chemistry. So you will go ahead. We just don't have time for fixing audio-video problems in real time here, unfortunately. So therefore, what I would like you to do is to go to nobelprize.org, chemistry laureates, on Popel, and actually watch that 5-minute segment of his interview that has to do with his feelings about electronic structure theory and advice to students on that topic. And then, if I could have the lights back on here in front, I will summarize his comments here. by saying that the goal of studying electronic structure of molecules is to try to get predictive power about molecular systems. And we want predictive power in terms of the 3D structure of molecules. Okay, so we know how to represent connectivity in molecules in 2 dimensions. We've been doing that already quite a bit this semester. But we would like to know if you know which atoms are bonded to which, then how does that translate into the intricate 3-dimensional structures that molecules can have? Also, molecules can have color. That's an important property of a molecular system. In addition to which, molecules can be magnetic. So magnetism is one of the important properties of molecular systems, and as they aggregate into extended solid materials, the way in which magnetic molecules interact to produce macroscopic magnetic phenomena is very much an area of interest to chemists. People want to design molecular magnets in order to be able to make materials that have desired properties that would be useful to us in building things. And then, of course, we have molecules that are redox active, and redox properties are very important. We would like to be able to sit down with our computer and draw out a structure. We would like to be able to pop it into its optimum 3D geometry and find out what that is. And we would like to then know how easy is it to remove an electron from that system, or how easy is it to add an electron to that system? Can we sit down and right from the start, can we use theory to predict properties like the energies associated with electron transfer to and from a molecular system? That would be important if we're going to do what I talked about last time in terms of inventing systems to transform light energy into chemical energy in terms of the water splitting reaction I discussed last time. Okay. Also, molecules have acid-base chemistry, and this is one of the most pervasive forms of chemical reactivity that we can discuss. And so we really have been talking about, so far in my lectures, about redox chemistry and acid-base chemistry. And as I go on, during the next few lectures, we're going to be also talking about properties like color and magnetism and 3D structure from theoretical considerations. Acid-base is one type of reactivity, but then also there are all kinds of different modes of reactivity that can be classified in different ways. Just to give you an example, there's a class of reactions in organic chemistry called electrocyclic reactions. So we will be talking a little bit about reactions of that sort. And then there's something that Professor Sayer referred to earlier in the semester as stability, and the idea that this can take on both kinetic and thermodynamic forms. And so we would want, from first principles, to be able to sit down and, considering a molecular system composed of whatever elements from whatever part of the periodic table it is composed of, just how do these properties follow naturally from the collection of elements that you've put together into a molecule? This is really chemistry, and this is what we'd like to be able to do. And so in this next part, what I'd like to do is I'm going to just spend a little time right here in 1957, because that's when Ronald Gillespie published his VSEPR theory. And Ronald Gillespie is now kind of in the twilight of his career. He has published on his quote-unquote lifetime in chemistry. And so you can Google Ronald Gillespie and find information about him and his VSEPR theory that will go well beyond what you'll find in that section devoted to it in your textbook. But this VSEPR theory, this is an acronym, and it stands for valence, shell, electron. Oh, repulsion. Thank you. Electron pair repulsion theory. I tell you, the closer you get to the board, the less easily you can see the things on that board. When we talk about VSEPR theory, Ronald Gillespie formulates it simply in terms of 5 basic considerations. And the first of these you can tell very easily from the name, and that is that electron pairs repel each other. Okay, and note here I'm underlining the word pairs, and that's because we know that electrons are all negatively charged particles, and so they should all individually repel each other, and they do in fact. But based on the ideas of Lewis, you'll see that Gillespie is formulating this theory, taking the notion of the electron pair as the fundamental unit to consider, and he's saying that electron pairs are somehow organized in space in a manner that they repel each other and they try to occupy different regions of space from one another. And this is going to be useful in terms of predicting the 3D structure of molecules. And this is what this theory is devoted to. And 2, we have molecules can have single bonds, or they can have double bonds, or they can have triple bonds between pairs of atoms. Maybe we'll see this semester also that molecules can have quadruple bonds between pairs of atoms if the orbitals are available for that. But in the VSEPR theory, in this context, multiple bonds are treated like single bonds. So you might suspect that that type of approximation is a little crude and that it might lead to certain guesses that might turn out not to be quite right, but actually it's a useful enough approximation for the prediction of the 3-dimensional structures of a lot of different molecules that we're actually going to adopt that for the purposes of our treatment of VSEPR theory. Number 3, if you have multiple central atoms, they're treated independently. And you'll see what I mean by that in a moment. You should see from that statement that in the context of VSEPR theory, we're going to be trying to identify central atoms and peripheral atoms that are attached all to the central atom. And there may be one or more central atoms in a molecule that themselves are interconnected. And 4, we have 2 kinds of electron pairs that we consider in VSEPR theory. We have lone pairs and we have bond pairs. And lone pairs occupy more space. Than bond pairs do. Okay, and we'll discuss the reason for that in a moment, but finally I want to give you rule number 5 for 3D structure prediction using VSEPR, and that is that lone pairs are not included in the description of the structure. And you'll see what I mean by that in a moment. The idea is that the names that we give to different molecular structures have to do with the 3D arrangement in space of the nuclei only, and not the electrons. Okay? So the lone pairs are not included in the structure description. This is reserved for the nuclei. Okay, so now let's do a couple of examples. And in introducing these examples, I'll also be giving you some more of the shorthand that's associated with VSEPR treatment of molecular structure. So let's talk about this one here. I've drawn here a very simple Lewis dot structure for hydrogen sulfide molecule, H2S. And for a molecule like this, we really only have two possibilities for the structure, because you got 3 nuclei. And so either they can all be arranged, we're going to assume that nuclei are not going to fuse together and be one on top of another. So because those positively charged nuclei do indeed repel each other very successfully. And so therefore, we could either have a linear or a bent structure. And we can approach that question using the VSEPR theory very nicely. We start out by recognizing that we have two lone pairs. That would be this one and this one in the Lewis dot structure that are not interacting with both hydrogen and sulfur nuclei. And we'll call those E. And then we have two bond pairs. And we'll refer to those each as X. And then we have a single central atom. We have a central sulfur atom. And the central atom is usually given the label A. And so that means that we have a system here of the type AX2 E2. And if you look at the general class of molecules of the type AX2E2, it turns out that we can draw their structures this way. So what I'm trying to indicate in this structure is that one of these lone pairs is coming up and out of the board this way, and the other one is going back behind the board the other way. These are two bond pairs that I'm representing as lines. Bond pairs occupy less space than lone pairs do, and that's because you have two electrons interacting with two positively charged nuclei, whereas in the case of a lone pair, you have a single pair of electrons interacting only with a singly positively charged nuclei. Two nuclei cause a greater localization in space of bond pairs as compared with lone pairs. And the angle here that this vector associated with the lone pair direction makes to the hydrogen is something approximately tetrahedral. Actually, probably larger than tetrahedral in this case because the HSH angle is smaller than tetrahedral in H2S. But this is an angle certainly greater than 90 degrees, and that is one of our angles of the type EAX that describes the interaction of a lone pair with a bond pair. So what we want to do is maximize those EAE and EAX angles because, as I was saying earlier, a lone pair of electrons requires a greater amount of space than does a bond pair of electrons. Okay, so the magnitude of the repulsions, if we get back to the word repulsion in the name of this theory, the greatest repulsions are found between lone pairs, and next we have repulsions between lone pairs and bond pairs, and then finally the weakest repulsions in the system will be between bond pairs. And so the best three-dimensional structure given by this theory is that which minimizes these different repulsions in the system. If we considered the linear structure, then what we would have to do is put all the electrons in the same plane of the molecule, and these angles here would have to be 90. And overall, this would be a higher energy structure because of the necessity of putting an E lone pair at 90 degrees to a couple of bond pairs, and so on around the molecule. So three-dimensionally in space, this quasi-tetrahedral geometry gets the four pairs of electrons in the molecule the farthest apart in space and minimizes electron pair repulsion, and that leads, therefore, to a description of the structure as bent. The structure is called bent rather than tetrahedral because we include only the nuclei in the way that we refer to the structure of the molecule, and we don't include those electron pairs. And let me give you a feel for how this looks. And in this picture that I'm going to show you, which will recall to mind some that I showed you in my first couple of lectures, you will see that what I've got here is an electron density isosurface for the H2S molecule. Okay, and you can see here one of the SH bonds. Here's another SH bond. Over here is that region in space where the electron density isosurface is associated with lone pairs. And you can see that certainly the electron density is a lot more tightly contracted in the region between the sulfurs and the hydrogens than it is elsewhere where it bulges out. And you can see that effect of getting the 8 valence electrons in this molecule as far apart from each other in space as you can. And then furthermore, the coloring in this diagram represents the propensity of electrons at that point in space to come together as pairs. In effect, that coloring is the three-dimensional manifestation of the Pauli principle mapped onto an electron density isosurface for the H2S molecule. Okay, so this type of picture is very nicely associated with the VSEPR representation of molecular structure. And I'm going to go through another example. And I'm going to bring this off so as not to distract you with that picture. And this next example is SF4. Okay, let me draw out a Lewis dot structure of this. as you're looking at this Lewis dot structure, one of the things you should do is to see if the number of electrons that I'm including in my drawing is in fact the correct number of valence electrons for this system. That's easy to do. You know that fluorine is in group 19 of the periodic table. You know that sulfur is in group 6 of the periodic table, and so you can quickly figure out how many valence electrons there should be, and hopefully I've indicated all of them on my drawing and no more than all of them. And what you might not like about a drawing like this is that while each fluorine has been represented as an octet, as being associated with 8 electrons, 4 pairs of electrons, the central sulfur atom seems to be, in this drawing, associated with 10 electrons, doesn't it? Okay, so that seems to be a violation of the octet rule, and I'll defer that observation for now, but it is an interesting feature of this, and when you do yourself write down Lewis structures as a prelude to subjecting them to the valence bond theory of Pauling or to the valence shell electron pair repulsion theory of Gillespie or the molecular orbital theory of Mulliken or the density functional theory of Kohn and Popel, you should be sticking with the basics here and making sure you're working with the right number of valence electrons, because your whole initial description of the molecular system is going to revolve around the correct distribution in space of this number of valence electrons that these atoms that you're including in the molecule bring into play. And then you're going to see if you can predict properties based on that. So that's what we do first. In terms of bond pairs, based on that structure, we have 4. And in terms of lone pairs, we've got 1. So therefore, the type of system that we're working with here is AX4E. Okay. This is one of the possible types when you have 5 units surrounding a central atom. And the most typical type of geometry that arises when we have 5 units surrounding a central atom is as follows. The atom A at the center is intended to be here. And then I'm going to draw 5 balls. You can think of them as representing either lone pairs or fluorine atoms. I'm going to color 2 of them to distinguish them from the others. And this structure is called TBP, and that stands for trigonal bipyramidal. And the reason I've colored this type different from that type is that in a trigonal bipyramidal structure, there are 2 possible environments, either for a lone pair of electrons or for a bond pair of electrons. You can have axial, and the axial position is easily distinguished from the equatorial position by virtue of the fact that an atom or a lone pair in the axial position makes 90-degree angles, 3 of them, to its neighbors, whereas an atom in the equatorial position makes 2 90-degree angles with respect to its neighbors. So it's 3 versus 2 that'll help you distinguish axial from equatorial. And understanding that about this molecular geometry, you can see that for the SF4 molecule, there are 2 possibilities. Note that when I'm drawing a wedge here, that means that the atom connected to the central atom is coming out of the plane at us, and the dashed bond means that it's going back behind the plane, so that viewed from the top, this thing would look simply like a Mercedes-Benz symbol. Okay? So just understand that about the wedges and dash nomenclature on these systems. And so the two possibilities that we have for our system is we can either put our lone pair E up here and our 4 bond pairs X down there, or we can have the lone pair equatorial and our bond pairs, 2 of them axial and 2 of them equatorial. So as in the case of H2S, we had 2 structures to distinguish between linear and bent. Over here, we have a structure with an equatorial lone pair or with an axial lone pair for SF4. And when you look at the top one and you realize that you have only 2 of these very bad lone pair bond pair contacts at 90 degrees, whereas on the bottom one we've got 3 of these bad lone pair bond pair contacts at 90 degrees, you might be inclined to pick, in fact, this top one. And that would be right, because it minimizes the number of the worst kind of repulsions, in this case, lone pair bond pair at 90 degrees. And when we give this structure a name, we're not going to call it trigonal bipyramidal because we don't include the lone pair. We only include the positions of the nuclei in the naming of the molecular structure. This one is called a seesaw. Okay, some of you may be aware that there is a piece of playground equipment known as a seesaw. You probably don't get a chance to play on them anymore very much, but neither do I. This is more fun anyway. And what I'm showing you now on the right on these side screens is a picture of the electron density isosurface for the SF4 molecule. And hopefully you can see that it looks like a seesaw. So these 2 fluorines down here would be the legs of the seesaw, and then you would sit either here or here, and then lean forward and put your hands on the lone pair, and then rock up and down somehow. I don't know. Anyway, in this system, you should be able to see that the lone pair on the sulfur, which is here, is in this definitely in this equatorial position. So the electron density isosurface has a nice dark blue color where we find that lone pair on the sulfur, and then the 4 fluorines are organized according to the predictions of VSEPR theory, with these 90-degree angles to the fluorines that are oriented in the axial, the 2 fluorines that are axial, and then here's our 2 equatorial fluorines here spinning around in the belt of this system. So we could also say that you would be sitting on the axial positions if you were going to ride on this particular seesaw. So now I would like to proceed in time briefly back from 57 to 1954, because we need to discuss some of the issues of valence bond theory that Pauling brought into the quantum mechanical treatment of molecules. What I'm representing here are a couple of hydrogen atoms 1s orbitals at a distance. We have HA 1s, and we have the 1s of hydrogen labeled B. And we're going to say that At some infinite separation between the two, they wouldn't really know much about the spin of the electron on the partner hydrogen, but as we bring them close together, the spin is going to become very important. And that's by virtue of the Pauli principle. And you should remember that one of the ways of formulating the Pauli principle is that no two electrons in a quantum mechanical system can have the same set of 4 quantum numbers. So as these two hydrogens get close together, the stable situation is for the electrons coming from the two to have opposite spin. So I'm drawing one with spin up and one with spin down. And then you're going to notice that here in the center of our H2 molecule now is a region of overlap and of constructive interference of those 1s orbital wave functions from the two sides. So in this representation of the ground state of the molecule, the Pauli principle is satisfied, and we can put this pair of electrons into an orbital, and when that orbital is represented that way, it is cylindrically symmetric. And we call that a sigma bond. In chemistry, we talk often about the properties of sigma bonds. We talk about also the properties of things called pi bonds, and we can even have delta bonds. Just as I was talking about bond multiplicity a moment ago with reference to VSEPR, let me give you here an XY plane. So I'm drawing in perspective an XY plane, and in this XY plane we're going to have actually 6 atomic nuclei. And our Z direction is perpendicular to this plane drawn in perspective. And I'm drawing in here the positions of 4 hydrogen and 2 carbon nuclei. And when I draw them in like that, you're going to see that all the orbitals of this system, all the valence orbitals of this system, except for 2, lie in that XY plane. And the 2 that lie out of that XY plane, I'll show you here, they are p orbitals that go above and below the plane. And I'm shading in the negative phase lobe of these pz orbitals. This is a pz from carbon A, and this is a pz from carbon B. And you can see that these are oriented in a side-on fashion, so that the overlap area that can occur is a side-to-side overlap of 2 neighboring p orbitals, like this. And the distinguishing feature here, as compared to my description of the sigma bond over there, is that it's not cylindrically symmetric. This bond has a nodal surface, which is the XY plane, where the phase changes as you pass from above that plane to below that plane. We have a nodal surface, a node containing the internuclear axis. So the type of bond that I've drawn there is distinct from a sigma bond. It's a pi bond. Okay, that bond over there, the sigma bond, has no nodal surfaces passing through the internuclear axis. So if I draw the internuclear axis here, you can see that it's got the same phase no matter where you are with respect to that axis. Plus, plus, plus everywhere. And here, if these lobes of these two pz orbitals are considered to be positive in positive z direction, then as we go this way, we pass through the xy plane and get down into negative z. We now have negative phase as indicated by the purple shading down here. The fact that that happens only once with respect to this internuclear axis is what tells us that it's a pi bond. If there were two such nodal surfaces, then we'd have a delta bond, and so on. And next time, we're going to start talking about the progression from these ideas onto hybridization, and then from there on to molecular orbital theory.